Lebesgue measure 0. So therefore it is f2 of x is equal to 1 almost everywhere. Therefore both essential supremum is equal to 1 and essential infimum is also 1. And let us look at another example. X is equal to the open interval 0, 1 and mu is equal to the Lebesgue measure. And let us define f of x to be equal to 1 by x. Then this f, one can easily verify that f belongs to LPx mu for 1 less than p less than infinity, but f does not belong to LPx mu for 0 less than p less than or equal to 1. This we can verify by directly integrating this function 1 by x over this interval, open interval 0 to 1, and you can verify this. This is direct integration will give you f belongs to LP for 1 less than p less than infinity, and f does not belong to LP for 0 less than p less than or equal to infinity. So we have defined the LP spaces in case of p is between 0 to infinity and also p equal to infinity. Sorry, we have not defined p is equal to infinity. Let us define now. Okay, so now we define the L infinity of x comma mu. It is defined as the set of all functions f from the space x to R such that f is measurable and essential supremum of mod f is less than infinity. That is, for other spaces, for p less than infinity or p is from 0 to infinity, 0 less than p less than infinity, we define LP of x comma mu to be set of all measurable functions from x to R such that integral over x mod f power p d mu is less than infinity, whereas in the case of p is equal to infinity, we define the space L infinity of x comma mu to be equal to set of all functions from x to R such that the essential supremum of mod f is less than infinity. That is, set of all measurable functions f from x to R such that essential supremum of mod f is less than infinity. So now we have defined the LP spaces for p is equal to p is between 0 less than p less than infinity. So now let us look at some important remarks. Okay, so we have defined the LP spaces to be the set of all functions from x to R such that f is measurable and integral over x mod f power p d mu is less than infinity. But you know that if two functions differ on a set of measure 0, then their integral remain the same. So therefore, in fact, this space, though we say they are functions, but they are not actually functions because two functions are equal almost everywhere, then they are treated as the same. That means we treat a class of functions together. That is, those functions which are all equal almost everywhere, they are all put together and form a class. So basically, LP of x comma mu is basically class of functions. And when you say an when you say an element of LP, it means a collection of functions together. They are all equal almost everywhere. But in practice, we take one member from each class for all practical purposes. Though they are classes, but still we take it as one member from the class. Okay. And so because of that reason, so elements of LP of x mu are not functions but the classes of functions. A zero element of this space LP x mu is set of those functions f such that f equal to 0 almost everywhere. Is again this class of functions all put together, we call it a zero function. Okay, and it is in fact it is meaningless to say the value of the function f at x because they are basically equivalence class of functions, but when we take basically one representative from the class. All right, is it clear?
Yes.
Yes. Okay, so whatever we have seen, now we have seen that okay, they are members of LP x mu, though they are they are collections of functions, but the functions which are equal almost everywhere, they are they form a class. And a zero function is basically set of those functions in LPx mu, they are all zero almost everywhere. All right. So now let us look at some of the natural questions. That is, the first question is, is this space LPX mu a vector space? And second question, is this LPX mu a metric space? And if you have studied a normed linear space in the linear algebra course, if you know what a norm is, then the question would be, is this space LPX mu a normed linear space? If you have not studied normed linear space, you need not worry about it, but you have studied metric spaces, so the question is whether this LPX mu a metric space. If it is a metric space, then the next question is this space complete? Is LPX mu complete? So this particular topic is all about these three questions. That is LPX mu a vector space? Is LPX mu a metric space? If it is a metric space, what is the metric that makes the space to be a metric space? And the next question is, that particular metric, is the space complete? Okay, so the first question is the space a vector space? Okay, that is our first theorem. In fact, this space is a vector space for 0 less than p less than or equal to infinity. So if you look at the set of all functions on the space X, it is obviously a vector space. You might have studied in the linear algebra course or in the first year when you studied algebra course. Okay, it is a vector space. But then in order to show this space LPX mu is a vector space, it only suffices to show that AF plus BG, that is A and B are say constants and F and G are members of LPX mu. It suffices to show that AF plus BG belongs to LPX mu for every FG in LPX mu and constants A and B. Now let us look at the case. That is, in order to show that LPX mu is a vector space, it is sufficient only to show that AF plus BG is in LPX mu for every choice of FG in LPX mu and every constants, every set of pair of constants A and B. Let us look at the case. There are two cases now, because P can be in the range 0 to infinity, 0 less than P less than infinity. Then it is very clear. We can easily check. Because F is in LPX mu, then AF belongs to LPX mu. That is, by directly computing the integral, you can directly check whether this AF, you can check whether the AF is there in LPU of mu or not. It is, in fact, it is there in LPX mu. Okay. So that means if G is in LP and F is in LP, then AF is in LPX mu and BG is in LPX mu. So in order to show this, all that you have to show is, if F and G are two functions in LPX mu, then only F plus G is in LPX mu. That is enough, because AF is always there in LPX mu if F is there in LPX mu, and BG is there in LPX mu if G is there in LPX mu. Okay. So in order to check whether AF plus BG is there in LPX mu, it is sufficient only to check where, if F and G are in LP or LPX mu, then F plus G is there in LPX mu. But you already know, if F is there in LP, then integral over X mod F power P d mu is less than infinity, and integral over X mod G power P d mu is less than. They are finite because they are in LP. Now let us look at mod F plus G power P. Let us get an estimate of this. This is less than or equal to 2 times maximum of mod F comma mod G. You can in the place of F and G, you can put mod F and mod G, maximum of mod F and G. So that means in the place of F you can take maximum of mod F comma G, and in the place of G also you can put maximum of mod F G. Then this is less than or equal to 2 times maximum of mod F comma mod G the whole power P. That is equal to 2 power P maximum of mod F comma mod